Welcome. In this section we're going to be talking about nonlinear systems of equations. So this is actually a continuation of the discussion of solving systems of equations that we've seen in earlier videos. Here we're going to be looking at nonlinear systems. So let's make sure we understand first what a nonlinear system is. So we say that a nonlinear system is just a system of equations in which at least one of the equations is nonlinear. And so what that means is that at least one of the equations that we have, if we were to look at the graphs, would not be a straight line. So we may see examples involving parabolas, circles, hyperbolas, the different conic sections that we've already discussed, because their graphs, of course, are not lines. But we could still have at least one line in our system. So to see how this works, let's go ahead and take a look at an example. Suppose I had the system, let's say x squared plus y is equal to 6. And x plus y is equal to 4. Well, I highly recommend that when we start solving a system of equations like this, where we have at least one equation that is not a line, that we graph the system first. And so that's what I'm going to go ahead and do here. And so to graph each of these equations, I'm going to rewrite them by solving for y in each case. So for the first equation, we would just subtract the x squared over. We'd have y is equal to negative x squared plus 6. And for the second equation, we would just have y is equal to negative x plus 4. So we should recognize that the first equation, its graph will give us a parabola, and the second one is a line. So this is still technically, though, a nonlinear system because we have at least one equation that is not a line. The first one, as we just mentioned, is a parabola. So let's go ahead and take a look at the graph of this system. So again, for our first equation, we have a parabola. It's one where the vertex would be at 0, 6, since we're just shifting the graph up 6 units. And it's opening downward. So it would be an upside down parabola that looks something like this. Then we also have the equation y is equal to negative x plus 4. That would just be a line. Its y-intercept would be at 4 here, and then we have a slope of negative 1, so just counting down 1 and over 1, you can see a graph that looks like this. And so just like with linear systems that we saw before, when we're trying to find the solutions to these systems, we're looking for the points of intersection. And so by graphing the system first, we can see that there are going to be two solutions to the system, because there are 2 points where the graphs intersect each other. So now our job is to actually figure out what those solutions are. What are the actual x and y coordinates? So in this case, we don't want to rely too much on the graph. I'm just kind of sketching it, so I'm just giving sort of an estimate of where the locations would be. It appears that one of the solutions will be in quadrant 1, the other in quadrant 2. But to find the actual coordinates, we need to go ahead and use algebraic techniques to find them. So there are a couple different ways we could do this. We could either do substitution or elimination, just like we had done with the linear systems in earlier sections. So I'll go ahead and do substitution on this one first, but then we'll also go back and look at elimination as well. So if I do substitution, I'll go ahead and use the equations as I wrote them when I was solving for y. And what I can do now is I can just take the expression that I have for y in one of the equations and plug it into the other one. And essentially that's just going to set the two equations equal to each other. So if I take the negative x squared plus 6, I know that that's equal to y. If I plug that into y in the second equation, then it becomes negative x squared plus 6 is equal to negative x plus 4. And so what we end up with here is just a polynomial equation in terms of x. So to solve this, we want to get everything on one side of the equal sign. We want to make one side equal to 0. So I will do that by adding x squared. I'll also go ahead and subtract 6 here. So adding x squared and subtracting 6 on the other side as well. And what we should be left with here is 0 is equal to, we would have x squared minus x minus 2. Then from here, this should be easy enough to factor. So we'll just factor as x minus 2 times x plus 1. And so our solutions for x are x equals 2 or x equals negative 1. Okay, but we're not finished yet. We're trying to find the actual x and y coordinates of the 2 points of intersection that we saw in the graph a moment ago. So to find the y coordinates here, I just need to recall that the y value we said was equal to negative x plus 4. So when x is equal to 2, we would have y is equal to negative 2 plus 4, which is 2. And so the actual coordinates that corresponds to is we're saying that x equals 2, and plugging that in, we get that y is equal to 2. So we have the point 2, 2. Then we also want to plug in x equals negative 1. So here we'd have minus negative 1 plus 4, which would just become 1 plus 4, which is 5. And so that corresponds to the point negative 1, 5. When x is negative 1, we get that y is 5. And if you go back and look at the graph of the system that we sketched earlier, we'll see that these 2 points are pretty close to the intersection points that we had sketched. Again, they might be slightly off because we were just sort of freehanding the sketch just to get an idea of where they would be located, but they would be pretty close. And so that should give us confidence that we have done things correctly here. Okay, so we could also solve this system by elimination, as I mentioned. We don't have to do substitution. We could use either method. So if I were going to do elimination, I would actually want to go back to the original way that the system was written. So remember we said that x squared plus y is equal to 6, and then we had x plus y equal to 4. And so just as we had done in earlier sections when we were doing elimination, I'll go ahead and call these row 1 and row 2 of the system. And so to solve this system, doing elimination, we can do that very easily by subtracting the second equation, or the second row, from the first one. So we'll do negative row 2 here, which would be negative x minus y is equal to negative 4. And so here we would have x squared minus x. Those are not like terms, so we have to just leave that as such. But the y terms would cancel. They would be eliminated, which is what we want. And on the other side, of course, we have 2. But here again, we end up with a polynomial equation. We'll have x squared minus x minus 2 equals 0. And this actually ends up being the exact same thing that we saw before. So we would have x minus 2 times x plus 1 equals 0. So once again, x equals 2, or x equals negative 1. And if you go back and plug those into one of the original equations, just like we had done before, we would get that the corresponding y values would be y equals 2 and y equals 5. So again, we end up with the solutions 2, 2, and negative 1, 5. So either technique works. You could do either elimination or substitution for each of these problems. It's really kind of up to you, but there will be certain situations where elimination might be easier and other situations where substitution might be easier. It just kind of depends on the problems. And we'll see examples of both in the upcoming examples. Now in the textbook, they may specify to use one method or the other. You can ignore that. Just do whichever method you think is best. A lot of the learning that's involved here is understanding when to use one method or another. And so looking for signs in the equations as to which method is going to be the preferred one. That's going to be something that you'll need to kind of practice with and try to develop that skill on your own. So always use whichever method you think is best. Don't necessarily use the method that the book tells you to do. Anyway, so let's go ahead and try some other examples here. So the next thing we'll take a look at is y is equal to negative quantity x minus 1 quantity squared plus 2. And for our second equation, we'll have y is equal to x squared minus 3. All right, so here we should recognize both of these equations as being parabolas. So let's go ahead and take a look at their graphs again. Again, I always recommend sketching the graphs of the equations first, because this can show us how many solutions there will be each time. So negative x minus 1 squared plus 2, this just goes back to the graphing techniques that we saw in earlier chapters. We'd be taking the standard parabola x squared, shifting to the right 1 and up 2, and it would be opening downwards, so the graph would look something like this. So that's our first equation. For the second one, you have x squared minus 3. So that would just be shifted down 3 units, and it would be opening upwards, so we would see a graph that is something like this. And so here we can see that there would again be 2 points of intersection for these curves. So it looks like we'll have one point of intersection in quadrant 1 and the other will be in quadrant 3. Now again, I don't want to rely on the graphs to try to determine the actual coordinates. That would only be reliable if my graph was super accurate. But since we're just sketching the graphs to get an idea of what the solution should look like, we're not going to have enough information on that just to get the actual solutions themselves. So we will need to decide which technique would be a better one to use to solve this. Do we want to do elimination or do we want to do substitution? So looking at the equations that I have here, I would argue that substitution would be a better way to go. Doing elimination would be rather difficult the way the equations are written. Hopefully it's pretty clear to see why that would be the case, but if not, you can always try doing elimination on your own. At any rate, so what we'll have here is negative x minus 1 squared plus 2 is equal to x squared minus 3. And this just comes from taking the y quantity that we have in the first equation and plugging that in for y in the second equation. Okay, so from here, what do we do? Well, I need to combine like terms as best I can, so I'm going to need to multiply this out. So remember that x minus 1 squared, that actually means x minus 1 times x minus 1. And so foiling this out, we'll have x squared minus 2x plus 1. And then we'll distribute our negative sign here, so we end up with negative x squared plus 2x minus 1, and then we still have the plus 2 there. So now I want to start combining like terms. So the way I will do that is I'm going to add x squared to both sides, first of all. So on the left-hand side, combining like terms there, the negative 1 plus 2 we can go ahead and combine. That'll be equal to 2x squared minus 3. And again, this is just a polynomial equation, so I want to get everything on one side of the equal sign. So I will subtract the 2x and subtract 1 from each side. So we will have 2x squared minus 2x minus 4, and all of that will be equal to 0. Okay, now before I go trying to factor this or use the quadratic formula or anything like that, notice that on the right-hand side, all of the coefficients are divisible by 2. So I'm going to go ahead and divide everything by 2 to simplify the equation, make it easier to work with. So this will give me 0 is equal to x squared minus x minus 2. And then that way it should be very easy to factor. So we should have x minus 2 and x plus 1 here. And this will give us x equals 2 or x equals negative 1. Okay, so now we need to find the y coordinates, and to do that I want to remember that y was equal to x squared minus 3, looking at the second equation from the original system. Again, I can use either equation, but I'm choosing this one because it's a little bit simpler to work with. So when x is equal to 2, we would have y is equal to 2 squared minus 3, which of course is just 4 minus 3, so it would be 1. And so that would correspond to the point 2, 1. And when x is equal to negative 1, we would have y is equal to negative 1 squared minus 3. So it would give us 1 minus 3, which would be negative 2. And so that would correspond to the point negative 1, negative 2. So those would be our solutions. And you can go back and look at the graphs that we saw earlier. These should be reasonable considering where we saw the points of intersection on that graph. Again, one of them was in the first quadrant and the other was in the third quadrant, and that's precisely what we see here. So again, this should give us good reason to believe that we've done things correctly. Okay, well let's take a look at some other examples. That was one doing substitution, so let's try an example where we do elimination instead. So what we'll look at here is the circle, x squared plus y squared equals 25, and the hyperbola, x squared minus y squared equals 1. So again, I always recommend graphing the system first, so we should understand how to graph each of these equations. Again, the first one is a circle, its center is 0, 0, and the radius would be 5. So hopefully we recognize that from our discussion of circles earlier. So the graph would look something like this. And then x squared minus y squared equals 1. That's a hyperbola. You could think of it as being x squared over 1 minus y squared over 1. So that would have its center at the origin. The a and b values would both be 1. So when you draw your central rectangle, it's just going to be this small square here. And of course we can use that square to draw in the asymptotes. Again, they're just the diagonals of that central rectangle. And since the x is first in the equation, the two branches of the hyperbola would open in the x direction. They would open left and right, as we see here. So it appears from my graph that I'm looking for 4 points of intersection. There are 4 points where these two graphs intersect each other, one in each quadrant. So let's see if that's what we get. Well, in this case, I would argue that doing elimination would be the easier way to go. Again, hopefully we see that substitution might be a little bit more challenging to do. But again, really that's more a matter of opinion than a matter of fact. So you could do either one, it's entirely up to you, but I would recommend elimination here. So here, just adding the two equations together right off the bat, we can see that the y terms would be eliminated. So they will cancel out, and what we'll have is 2x squared is equal to 26. This, of course, gives us x squared equals 13. So taking the square root of each side, we should have x is equal to plus or minus root 13. So here we end up with irrational solutions for x. Now, we still need to figure out the y coordinates here, so I want to take these values and plug them back in. So I'm going to take these x values that I got and plug them back into one of the original equations. Again, I could use either one. I'll go ahead and plug into the first one, but what I'm actually going to plug in here is not the x equals plus or minus root 13. I'm going to use the x squared equals 13. So if I go back to the first equation, which was x squared plus y squared equals 25, I want to replace x squared with 13. So that's the easier way to go about this problem. Don't plug in the plus or minus root 13 for x. Just plug in what we know for x squared, since that's what's contained in the original equation anyway. Well, from here, we can, of course, just subtract 13 on each side, so we end up with y squared is equal to 12. And so this will give us y is equal to plus or minus the square root of 12, which of course reduces to plus or minus 2 root 3. And so our solutions here, there are 4 of them. We can go ahead and write this as just plus or minus root 13, comma, plus or minus 2 root 3. That's a perfectly acceptable way of writing the solution. But bear in mind that we do actually have 4 solutions here. So if I were to write them out individually, we have the point root 13, comma 2 root 3. That's from quadrant 1. Then we have negative root 13, comma 2 root 3. That's the point in quadrant 2. Then we have negative root 13, negative 2 root 3. That's the point in quadrant 3. And finally, we would have root 13, comma negative 2 root 3. And that would be the point in quadrant 4. So we do have 4 solutions, looking at all the different combinations of plus and minus signs that we can have for the x and y coordinates here. You do not need to write them out as 4 individual solutions like I've done here. I'm only doing that for your benefit so you can see the actual points of intersection and how that corresponds to the 4 points that we saw in the original graph. But feel free to just leave it in the plus minus notation. You don't need to write it out as 4 separate quantities. Okay, well, in addition to elimination and substitution, there are certain situations where only using the graph will be necessary to actually solve the system. Most of the time, the problems will be like the ones that we've seen here, where we have to actually use substitution or elimination to solve. But let's look at some other examples where we may not have to do that. So suppose I had the system, let's say x squared plus y squared equals 4. And let's look at the equation x squared over 9 minus y squared is equal to 1. So hopefully, hopefully we'll recognize these graphs as being that of a circle in the first equation, and the second one is a hyperbola. So let's again go ahead and graph these equations. So x squared plus y squared equals 4. That would just be a circle centered at the origin with a radius of 4, or excuse me, with a radius of 2, so going 2 units in every direction. So we're looking at that circle there. The second one, again, is a hyperbola. In this case, the a value is 3, so we go 3 units to the left and to the right. The b value is 1, so we go up 1 and down 1 to draw our central rectangle. Remember, the diagonals of that rectangle give us the asymptotes of the hyperbola. So if we draw in the actual branches, again, they'll be opening left and right because the x term is first in our equation, so we see a graph that looks like this. So when we're looking for the points of intersection, we want to see where the circle and the actual branches of the hyperbola intersect each other. I'm not interested in whether or not the asymptotes of the hyperbola intersect the circle. I just want to know if the branches themselves do. And hopefully it's pretty obvious from this graph that they do not. So if the two graphs do not intersect each other, then that tells us that there is no solution. At least no real solution. But we're only going to be interested in real solutions here. We're just looking at points of intersection of the graphs. So in this case, I can solve the entire system by looking at the graph only. I don't actually need to do anything else. At this point, technically, I'm done with the problem. I know there's no solution. I can go ahead and write the answer as such and move on to the next problem. Now, some of you might wonder, well, what if we didn't graph it, or if we forgot to, or something like that? Would we still be able to get the correct answer here? And the answer to that, of course, is yes. And the way I'll show that here is I'll go ahead and mark this as, let's call this row 1 here, and row 2, and I'm going to go ahead and do elimination. And you might think that doing elimination here would be easiest just to go ahead and add the two equations together to cancel the y squared terms. And you could do that. But actually, it's going to be easier here if we eliminate the x terms, which I know may seem strange, but that's how I'm going to go ahead and approach the problem here. So we're going to leave row 1 the way it is. Row 2, then I'm going to go ahead and multiply by 9. Or excuse me, negative 9. So what we'll get there is negative x squared plus 9y squared is equal to negative 9. So I'm actually eliminating the x's here, not the y's. And what I would get is 10y squared is equal to negative 5. So solving for y here, we would have y squared equals negative 1/2. And by taking the square root of each side, what will happen is we're going to end up taking the square root of a negative number. So we end up with imaginary solutions in this case. Again, we're only going to be interested in real valued solutions, so when this happens, we can just say no solution. Or if you want to be more specific, you could say no real solution. But this shows us by doing the elimination process that we're not getting a solution, but we can see that, I think, more easily just by looking at the graphs of the two equations. So again, I always recommend graphing first, because in a situation like this, it would actually allow us to conclude that there's no solution without having to go through this elimination process. So that would be my recommendation there. But if you prefer to do the elimination, that's fine. But I just think that graphing would be easier. Anyway, let's go ahead and take a look at some other examples like this. What if I had the system, let's say y squared is equal to negative 4 times x minus 1. And let's look at x minus 3 squared plus y squared equals 4. Well, here hopefully we'll recognize that the graphs are a parabola and a circle. The parabola, it would be one that would be opening to the left because you have a y squared term, and the p-value is negative in that case. Hopefully we can also tell that we have a vertex at the point 1, 0. So the vertex would be at 1, 0, and it would be a parabola opening towards the left. The circle, on the other hand, its center is at 3, 0, and it has a radius of 2. So if I sketch the graph there, we'd be looking at this circle that we see here. Well, here the two graphs do intersect each other, and it should be easy to tell just based upon the graphs that they intersect each other at the point 1, 0. And so that would end up being our solution. Now again, we could obtain that solution by doing substitution or elimination here. But I would say that that's going to make the problem fairly complicated if we go through all that. Hopefully sketching the graphs here is not too difficult if we understand the graphing techniques that we studied when we were looking at the conic sections. So if you are able to determine the points of intersection just from the graphs, you can go ahead and use that as your solution. There's no other work that needs to be shown here. But again, we do want to be careful about this because most of the time the graphs are not going to show us the points of intersection accurately. In this case it does because the two graphs happen to intersect at just one point. But the idea here is that when we graph the system, a lot of times it can tell us if there is just one solution like this and what the point of intersection would be, or if there's no solution like we saw in the last example. And of course, with other examples that we saw, it's a good idea to graph because it will tell us the total number of solutions that we'll have and also what quadrants they would be located in. So again, you can use elimination or substitution, but don't forget to graph each time whenever possible, because that can tell you a lot of information about the solutions as well. But that concludes our discussion for nonlinear systems.